Example 3 in 9.1 throws a bit of a twist at us. It gives us a graph and it wants us to come up with an inequality to represent that graph. You really, as a class, you guys did great on this in I think it was chapter 7, where you had to come up with an equation of a linear line from 2 points. And all we really need for a linear line is 2 points or a slope and a point. And I would argue it's much, much better to find a slope here, or sorry, a point here and a point here. So the 2 points on this curve that I see are 0, 1 and 1, 3. Now, some of you may be able to eyeball that and notice that that does mean we have a slope of positive 2. And that's awesome if you can do that. But if you can't do that, that's fine, because we can use our slope formula. Our slope formula tells us that the slope is 3 minus 1 over 1 minus 0, which is equal to 2 over 1, which is just 2. So we find that either visually or mathematically. Knowing the slope and the point is enough. I am a big fan of using y equals mx plus b. It depends on what you're comfortable with. I'm going to use y equals m plus b, and we know what b is. B is 1 because that's the y-intercept. But I want to show you it works regardless. So this is y equals 2x plus b. And we know it goes through the point 1, 3. So if I put 1, 3 into that, I get that 3 is equal to 2 times 1 plus b. 3 is equal to 2 plus b. When I subtract the 2, I get that 1 is equal to b. Now, what this means is that dotted line can be represented by y equals 2x plus 1. But I really want to make it clear that that is not an inequality. That's an equation. So what we need to determine is to make this an inequality, I need to put an inequality symbol is, and we have 4 choices: greater than or equal to, less than or equal to, greater than or less than. Fortunately, 2 of those choices are very clearly wrong. Try to take a look at the graph and look at the 4 inequality symbols that I just wrote out. Which 2 of those can it not be for sure? What do you notice about the nature of that straight line on the inequality? Hopefully you notice that it was a dashed line, and because it's a dashed line, it cannot be greater than or equal to or less than or equal to. Now, the nice thing about y equals mx plus b, and I want to write this, is that if it's y is greater than mx plus b, you shade above. And this is the nice thing about isolating y. If it's y is less than mx plus b, you shade below. And that's one of those nice things that, there is a reason why I push y equals mx plus b, is it does have that's kind of slight little shortcut. Now, looking at the graph, I think pretty clearly we shaded in above the graph. So it should mean that y is greater than 2x plus 1 is our solution. But don't take it on just kind of blind trust that I'm correct. I would then choose a point that's clearly in the solution region, and I'm going to choose this point right here, negative 4, 0, and I would plug it into my inequality to make sure that I did it correctly. Because if I did it right, when I put negative 4 in for x and 0 in for y, it should satisfy the inequality that I've written. And when I do that, I get that 0 is greater than 2 times negative 4 plus 1, which is 0 is greater than, that's negative 8 plus 1, so 0 is greater than negative 7. Is 0 greater than negative 7? Definitely. Right? 0 is to the right of negative 7 on a number line, so this is true, which means that that should be a part of our solution region. So y is greater than 2x plus 1 is correct. Now, there is a nice, and again, it's not a cheat, but it's an exploitation of our calculator that we can use. If you want to make sure you did that inequality correctly, this is only going to work on your calculator if you have y isolated. But what you need to do is you still type in y is equal to 2x plus 1, but then you put your cursor to where this little slash is. And what this is the type of line my calculator is going to use. Now, unfortunately, this is a TI-84 color, so it's going to come up with a little menu. If you're using a TI-84 Plus or TI-83, you're probably just going to have to hit enter until you get this symbol to be the upper triangle. Now, it's reason it's the upper triangle is that is telling the calculator to shade above the curve in. And then to make sure that it looks at least reasonably like we saw in the notes, I'm going to go back to Zoom Standard, and my calculator is actually going to graph that line for us. Now, the one thing that the calculator cannot do for us, and I love that it cannot do this, is it cannot actually do a dotted line. Well, it can do a dotted line, but it won't shade at the same time. So this is a great way to ensure that we did the shading properly, and then just keeping in mind that if y is greater than mx plus b, we shade above, and it's the little triangle I used on my calculator. If y is less than mx plus b, and I'll show you that here maybe, If I wanted to see what it looked like if it was less than that value, and I'm sure you can imagine this is just going to shade in the other half of my Cartesian plane. But if I switch that to the kind of lower triangle, I went the wrong direction, but that's okay. Right there, I'll get it. Then when I hit OK and graph again, the blue line is if it's greater than, and the red line if it's less than. And we see that those inequalities together form every single coordinate on the Cartesian plane, which I think is an important consideration. Using your calculator like this is really handy later on in Chapter 9 when we start to talk about the overlapping section of multiple inequalities. And we're going to see a little bit of that in the last example coming up.